Hey there, here we are continuing on with our series tests. Today we're talking about 11.5 alternating series. Any series that can be written in the form -1 to the n power times bn, or -1 to the n minus 1 power times bn, where bn is a positive sequence, is called an alternating series. So for example, we might have something like n equals 1 to infinity, -1 to the n times n squared. And what this would look like would be, well, if n was 1, this would be -1 to the 1 power, so it would be negative, and then 1 squared is 1. Plus, if n was 2, this becomes +1, and it would be +4. If n is 3, we get -9. So we can see that the terms alternate between positive and negative. +16, -25, +36, forever. Right, so the -1 to the n power alternates the terms between positive and negative. This piece of the pie right here is positive. Bn would be the sequence n squared, which is clearly positive for all values of n. The difference between -1 to the n and -1 to the n minus 1 just determines if the first term is negative or positive, and then alternates accordingly. So let's suppose we had -1 to the n minus 1, and then we had 1/4 to the n power. Okay, so this would be, well, if n was 1, so back to my starting point. If n was 1, it'd be -1 to the 0 power, which would be +1, and then 1/4 to the 1 power, which would be 1/4. And then if I put 2 in here, 1/4 squared would be 1/16. But 2 minus 1 would be +1, so it'd be -1/16. And then it would be +1/64, minus so forth and so on. So the terms would still alternate. This is what we would identify as the part of the sequence that's not alternating, 1/4 to the n. And clearly those are all positive for any value of n, and it alternates this way. So if it's -1 to the n minus 1 power, the first term will be positive if we start at 1. If it's -1 to the n power, the first term would be negative. Note, sometimes we see this instead. We'll see -1 to the n plus 1. Notice for any value of n, -1 to the n minus 1 is equivalent to -1 to the n plus 1. So either one of these can be used interchangeably. We could actually even change this to 3, right? Because if we put in 2 here, for example, it would be 2 minus 1 would be 1. We put in 2 here, it would also be an odd power. So there's different ways to express alternating series, but this is just generally how we do it. Right, if we have a series that alternates, we have a test to see if that alternating series converges. So we have a series that alternates. We have to pull out the part that's positive. If bn is decreasing, if the sequence is a decreasing sequence and the limit of this decreasing sequence is 0, then the given alternating series converges. So the proof of this is in your textbook. You can also Google it. Lots of videos on the proof of this. If anybody wants to discuss the details, I would be happy to go over that. But let's take a look at this guy right here. -1 to the n minus 1. All over n. If we write this out, if n is 1, we get -1 to the 0 power, which is 1 over 1. And if n is 2, it's -1 to the 1 power, which is odd, so my next term is going to be odd, 1/2, and then we're going to have 1/3, 1/4, whoops, no, -1/4, right? Minus plus minus, and then it would be +1/5, so forth, -1/6, plus so forth and so on. Right, so if you recognize this, this appears to be similar to the harmonic series. It in fact is a form of the harmonic series. It's called the alternating harmonic series. Now remember, the harmonic series, not alternating, if we just had 1 plus 1/2 plus 1/3 plus 1/4 forever, it would diverge. This actually doesn't behave the same way. This actually is going to converge. If we looked at the series of partial sums, or the sequence of partial sums, we would see that the sequence does converge, but we're going to use this alternating series test. So we have to check, let's put it in the necessary form, and check the hypotheses of the series test. So we first need to write it as n equals 1 to infinity times 1 over n, just to identify. And you don't, once you get good at this, you don't need to write out all these details. But this would be the corresponding sequence. This would be Bn. So that's what we have to investigate. So it's -1 to the n minus 1 times the terms of the sequence Bn, which is the harmonic series. First thing we have to ask ourselves, is Bn decreasing? So is this corresponding sequence decreasing? So we want to show that Bn plus 1 is less than or equal to Bn. Well, that's pretty easy for the harmonic series, because n plus 1 is definitely bigger than n for any value of n. If we take any value of n and add 1 to it, it's going to be larger than itself. So then we use the property of reciprocal, so 1 over n plus 1 is clearly less than 1 over n. So this would be the n plus 1th term, which is less than the nth term. So therefore, the sequence 1 over n is decreasing. And 2, the limit, as n goes to infinity, of 1 over n is 0. So both criteria hold. Therefore, by the alternating series test, -1 to the n minus 1 times 1 over n from 1 to infinity converges. Remember, the tests don't give us the value of this sum, but it does tell you that a finite value does exist. Right, so keep in mind you have to show that the sequence is decreasing, the corresponding sequence is decreasing, and that the limit is 0. If the corresponding sequence is not decreasing, then this test is inconclusive, or perhaps the corresponding sequence is decreasing, but the limit is not 0, then this test is inconclusive. We can't conclude that it doesn't converge, we just can't conclude anything. So if these two criteria hold, then the corresponding series converges. If one or both of these don't hold, the test is inconclusive and we have to go to a different test. So this one is pretty simple. Be careful, because sometimes we have alternating series in disguise. You might look at this and be like, oh my goodness, not even sure where to start. But when in doubt, sometimes it's not a bad idea to just write out a few terms of the series. So if you notice, let's write this out. If n is 1, we get the cosine of pi over the square root of 1. So the cosine of pi over 1. And then if n is 2, we get the cosine of 2 pi over the square root of 2, plus the cosine of 3 pi over the square root of 3, plus. So now let's evaluate this, because the cosine of pi actually has a numerical value. The cosine of pi is -1, so this is -1 over 1. The cosine of 2 pi is +1, so plus 1 over the square root of 2. Cosine of 3 pi bounces back to negative. And then 4 pi is going to behave like 2 pi, so it's going to be 1 over the square root of 4 minus 1 over the square root of 5, and it's going to behave like this. So this actually is another way of saying -1 to the n times 1 over the square root of n. And n goes from 1 to infinity. And notice I use the power of n because at 1 I want the first term to be negative, so I need just plain old 1 there. So this series is equivalent to this series, so it is an alternating series. This is Bn, right? So let's show 1 is Bn, 1 over the square root of n decreasing. There's two ways you can do this. You could look at the equivalent function, take the derivative of 1 over the square root of x and see that it's always negative for positive values. Or algebraically, this is pretty simple, because is the n plus 1 term less than the nth term? Well, let's see. We know that n plus 1 is greater than n. So the square root of n plus 1 must be greater than the square root of n. And then we just use our reciprocal properties. So there we just showed that bn plus 1, the n plus 1 term is less than the nth term. So it is decreasing. And now we just have to take the limit, and if both those conditions hold, and we know that the limit as n goes to infinity of bn, which in this case is the limit as n goes to infinity of 1 over the square root of n, is 0. So both conditions hold. Therefore, by the alternating series test, the cosine of pi n all over the square root of n equals 1 to infinity converges. All right, so there's not much more to this section. I'm going to have you read this, work on some problems. Please make sure you are checking Blackboard for my posted Zoom hours. XYZ 5.5 homework. Be sure to check Blackboard. For updates and Zoom hours. Would love to do problem solving if anybody's interested in working on some series and would like to set up a time. Monday or Wednesday at 12:30 is always good for me. Actually, I take that back. I'm not sure about 12:30. My department's been having meetings, but maybe at 1:30. So let's talk about that. Let me know how you're doing. Hope everyone is doing well and not going too stir crazy. All right, stay tuned for our last set of tests. See ya.